Two more big calculus rules coming at you, the product and quotient rules. The product rule is a little simpler to use, so we're going to start with that one. And it refers to what to do if you're taking the derivative of a product of functions. So before with the sum rule, we said if you have a sum of two functions, f and g, to differentiate that, you just go term by term and just do them separately. Unfortunately, it doesn't work that way with the product of two functions, with one function times another function. So here's how it does work. It says, given two differentiable functions, f and g, the derivative of f of x times g of x is f of x times g prime of x plus f prime of x times g of x. So in plain terms, if the derivative of a product of functions is the first function times the derivative of the second function plus the derivative of the first function times the second function. Okay, so it's not just f prime times g prime. Be great if it was. That's just not how it works out. This isn't hard to prove using the just the definition of the derivative and trying it on a product, but it gets a little into the weeds, so I'm not going to do it. I'm just going to kind of demonstrate that, yes, this is in fact how it works. So I'm going to just constantly emphasize, don't just do both derivatives. It has to be this. So it's one times the derivative of the other plus the other one times the other, like that. Okay, not just the product of the derivatives. Sorry. So let's just do an example. Let's just see it in action and just everybody agree that, oh, that seemed to work. So in real life, if I asked you to find the derivative of x squared times the cube root of x, you would not use the product rule. You could, but I wouldn't want you to. And I wouldn't if I was you. I would just say, okay, that's x squared times x to the 1/3, add the exponents together, and do it just using the power rule. So we really don't need the power rule at all at this point in the class. We're just busting it out. Because you can, everything we have so far, you can just use exponents to combine. So we'll do it both ways. And you'll see which way is quicker, but you'll also see that, hey, at least it works. So we're just going to try it with the product rule. So the product rule says that it's the first function, x squared, times the derivative of the second function, x to the 1/3, plus the derivative of x squared times the second function, x to the 1/3. So you see this rule makes copies of the original functions, right? We're going to have a copy of x squared and we're going to have a copy of x to the 1/3 in our final result, whatever that looks like. That's x squared times 1/3 x to the negative 2/3 plus 2x times x to the 1/3. So that's the answer, but it's ugly and it can be simplified, and that's again why I would say don't use the product rule here. This is just an example. So we're going to just combine exponents. The first term is 1/3, and then it's x squared times x to the negative 2/3. So you add those exponents. 2 plus negative 2/3 is 6/3 minus 2/3, which is 4/3. Right, so that's the first term. The second term is 2 times x. Okay, so that's actually x to the 1. So 1 plus 1/3 is 4/3. So I'm being a little fast and loose with the algebra here, but that's because, you know, you have to be able to do this stuff pretty fast too at this point. So those terms, they now have the same exponent, so they just, you can combine them. 1/3 x to the whatever plus 2x to the whatever. You just add the 1/3 and the 2. So you get 7/3 x to the 4/3. So that's the final simplified result. So that's what the power rule is telling you that the answer is. Let's try it the other way, because I just want you to see that, hey, it works. You get the same result. So this, again, this is the way I would prefer you to do it. Don't do it the first way. That's just an example. If you see something like this, do it this way. Don't use the product rule unless you have to. So x squared times x to the 1/3 is x to the 7/3, because 2 plus 1/3 is 7/3. So before you do the derivative, simplify what's inside. And that's a good general rule. If you can simplify what's inside a derivative before you do it, because then the differentiation is easier and your answer is simpler. And look at that. I mean, you can do that in your head. The derivative of x to the 7/3 is 7/3 times x to the 4/3. 7/3 minus 3/3. Okay, so everybody, hopefully you agree that way is faster and better. But rather than proving the power rule, the product rule, I'm just giving you one instance where it worked, and we're just going to take that as, okay, that's proof and it's good enough. Okay, and emphasizing again, you do not just multiply the derivatives. I wish you did, but you don't. So it's not 2x times 1/3 x to the negative 2/3. You don't just take the derivative of both functions and multiply them together. Invariably, somebody's going to do that. And now you can't say I didn't tell you multiple times not to do that. That's just not how it works. And you can see that that thing that we have there is not the answer. It's not 7/3 x to the 4/3, right? It's something totally different. So, right, you know that it doesn't work like that. So what we really, the reason I say we don't really need the product rule at this point in the course is because we don't have different types of functions. If you have, right, like x squared times sine of x, those are two different types of functions and they don't combine in any meaningful way. There's no way to simplify that expression. So you need the product rule for that because while we have the individual derivatives for them, no problem. So then you just need the product rule. So, right, if you had like e to the x over the square root of x or something, you would need one of these rules because those are two different types of functions. And then the nice thing about this is since addition is symmetric and multiplication is also symmetric, it doesn't matter which way you remember the power rule. So if you did have to memorize this and you think, okay, it's f prime times g plus f times g prime. If you got that backwards, you'd still be right. Because if we did g prime times f plus f prime times g, it would still be the same thing because addition is symmetric, which should make sense because f times g better have the same derivative as g times f because multiplication works both ways. So you don't have to remember which order these two things go in. I just say it this way because it's what I'm used to. You can think about it the other way, and it's the exact same thing. Okay, so this one's a little nastier and a little harder to remember, but we do need it. So here it is. That's the quotient rule. Given two differentiable functions, f of x and g of x. G of x cannot be 0. If it does, this formula does not apply. The derivative of f of x over g of x is this thing. So it's g of x times f prime of x minus f of x times g prime of x all over g of x squared. I know that looks complicated, but calculus students since the beginning of time have had to memorize this formula, so don't complain. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So note that you can't mix this one up backwards, unfortunately, because subtraction is not symmetric, and g over f isn't the same thing as f over g. So if you do the top times the derivative of the bottom first, it's backwards and it's going to be wrong. So be careful with that. However you remember this, right? So just you can remember that bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. There's this stupid little rhyme that I'm going to put up on the screen and not even say. So d high means the derivative of the top, and d low in this little rhyme means the derivative of the bottom, right? So it's low times the derivative of the top minus high, meaning the top thing, times the derivative of the bottom over the square of the bottom function. All right, I know it's dumb, but it works, and I'd be lying if I said I didn't run it over in my head sometimes when I'm trying to remember which way it is. So you all know what the best way to memorize things is for you. This being an online course, I can't really make you memorize it anyways, but you do have to use it a lot and you have to use it fast. So it's important that you're just familiar with it. So let's just dive in and do examples. We do need the quotient rule at this point in the class. There's stuff that we absolutely need it for, that unlike the product rule. Right, so emphasizing the order does matter. It has to be the bottom times the derivative of the top first. If you just use the product rule on f of x times 1 over g of x, that's the same thing as f of x times g of x. This is just what you get. So the quotient rule is just a version of the product rule where instead of just g, you have 1 over some function g. So that's why it looks more complicated. It is more complicated. There's more stuff in it. But that's where that g squared thing looks weird on the bottom, but it just comes right out of that. And again, emphasizing, don't just do the derivatives separately. It'd be great if it worked like that, just f prime over g prime, but it doesn't, because it's complicated. Once you start dividing functions by other functions, you get very complex functions. So in general, for most things, derivatives tend to kind of get more complicated. The derivative of a complicated function is usually a much more complicated function. Usually, we'll see exceptions. Okay, so this is what I mean. We need it for something like this. There's no meaningful way to simplify that thing inside the derivative. You can't factor it and simplify it. You can't split it up. If there was only one thing in the denominator, you could split it up into separate terms, but there's not, so you can't. So there's no way to do it. It just is what it is, and we just have to use the quotient rule. So at least at first, it's good to write down, okay, what f is and what g is. Same with using the product rule sometimes. If you just make a little chart and you say, okay, f is this and g is this. You can even say, okay, then f prime is this and g prime is this. And then you can just kind of stick everything where it goes. You have all the ingredients and you say, okay, this goes here and this goes here and this goes here and this goes here. So f is your top, g is your bottom. So here it is. It's g, right, times the derivative of f minus f times the derivative of g all over g squared. So it looks awful, but as long as you know where to put everything, there's really nothing new here. It's a lot of stuff and it looks complex, but we don't really have to do anything with it, so who cares? It's just a big complicated math expression. So all we have to do now is two derivatives of stuff that we know how to take the derivative of. So the derivative of x cubed minus x is 3x squared minus 1. Don't forget the derivative of x is 1. That one screws people up. And then the derivative of 3x squared plus 5x minus 2 is 6x plus 5. That minus 2 goes away when you take the derivative. And then the denominator is just the original denominator squared. It's not, you don't do the derivative in the denominator. So this is another case where I could ask you to multiply all that out and simplify it as much as possible, but I absolutely will not. And in fact, I'll be mad at you if you do. So don't do that. Just leave it like this. I know it goes against your instincts. You want things to be simple and clean and compact, but there's really no reason to, and there's no promise that it would really simplify. There's no reason to think it would simplify in any meaningful way. So I know that looks awful as an answer to leave on a math test or whatever, but that's the way I'd like you to leave it. It's easier for me to tell what I'm looking at. And also, every little thing you do to simplify it is another opportunity to make a mistake. So you'll feel bad if you get the right derivative, and then by needlessly simplifying it, you screw it up and then you lose points for something you didn't even need to do in the first place. So if you do it exactly right, and I can't punish you, unfortunately, but I'm trying to instill into you now just to leave stuff like this. Some of these, we're going to see derivatives that are way uglier than that, okay? And I still want you just to leave them how they are. Word of warning on the quotient rule, it's tempting to use it on something like this because it is a quotient and it would work. But again, don't. Just do what we said before with just power rule stuff. 5 over x cubed is the same thing as 5x to the negative 3. And the derivative of 5x to the negative 3 you can do in your head, right? It's just negative 15x to the negative 4. So don't get all excited and use our fancy new rules in places where you don't have to. You're going to get a much cleaner answer just doing it this way. You're welcome to go back and try it using the quotient rule. It does simplify to being the same thing, but it does take some simplification. So just always think, is there a way to make this easier before I do the derivative? I want to give you one more example. This is just 1 over a function. But we do need the quotient rule for this because there's no way to simplify that 2x squared plus 3, and it can't be split up the same way that a numerator can. So we just have to use, as our f of x is just 1, and our g of x is 2x squared plus 3. So we're going to have the derivative of 1 is just 0. So we're going to have some 0 stuff in here. Just, again, don't think that it's just 1 over the derivative of 2x squared plus 3. It's not that simple. These functions have asymptotes. They're complicated. So the derivatives are even more complicated. So there it is. It's 2x squared plus 3 times the derivative of 1 minus 1 times the derivative of 2x squared plus 3 all over 2x squared plus 3 squared. So when I say not to simplify, don't leave it like that because we haven't even done the derivative yet, and that's the whole point of this course, is to do derivatives. Right, the derivative of 1 is 0, so that whole first term is going to drop out. If you're comfortable with that fact, you could probably have just skipped writing that down even. And then we have a 1. The derivative of 2x squared plus 3 is negative 4x. And that's it. So, you know, when things are just 0, yeah, get rid of them. So do maybe real common sense simplifications like that. And if it's ever not clear, just ask me like, hey, is this good enough? Do you need me to take this further? I'd rather see you just leave stuff how it is. So there it is. That's the derivative of 1 over that function, 1 over 2x squared plus 3. And we can kind of think about a version of the quotient rule. If it is just 1 over a function, if f is just 1, then the same thing always happens, and it's what you see, what you just saw happened. It's negative g prime over g squared. So don't think about that as a new rule that you have to memorize. It's just a very specific instance of the quotient rule. And we're going to see stuff like that, stuff that keeps popping up throughout the course, like what's the derivative of a function squared. It's just good to see the pattern and see that the same thing always happens. But if you just do the math and use the rules that you're supposed to use, you're going to get that thing. So that's just something, right, that you're just going to see a lot throughout throughout calculus.